Good morning everyone. I am here before you to give a small presentation on the topic boundary layer concept and a problem based on that. For defining the boundary layer, consider the flow of a fluid having free stream velocity u over a smooth thin plate which is flat and placed parallel to the direction for free stream of fluid as shown. Let us consider the flow with zero pressure gradient on one side of the plate which is stationary. The velocity of fluid on the surface of the plate should be equal to the velocity of the plate. But plate is stationary and hence velocity of fluid on the surface of the plate is zero. But at a distance away from the plate, the fluid is having certain velocity. Thus, a velocity gradient is set up. This velocity gradient develops shear resistance which retards the fluid. Fluid with a uniform free stream velocity u is retarded in the vicinity of the solid surface of the plate and the boundary layer region begins at the sharp leading edge. At subsequent points downstream the leading edge, the boundary layer region increases because the retarded fluid is further retarded. This is also referred as the growth of boundary layer. Near the leading edge of the surface of the plate, where the thickness is small, the flow in the boundary layer is laminar, though the main flow here is turbulent. This layer of the fluid is said to be laminar boundary layer, and this is shown by AE in the figure. And we have AB as the laminar zone. Reynolds number is given by ux by v, where x is distance from leading edge, u is free stream velocity of fluid, and v is kinematic viscosity of fluid. We have Reynolds number equal to 5 into 10 raised to 5. So we have the equation 5 into 10 raised to 5 equal to ux divided by v. Hence, for laminar boundary layer, 5 into 10 raised to 5 equal to ux by v. If u and v are known, x can be easily calculated. From laminar boundary layer, now let's move on to turbulent boundary layer. If the length of the plate is more than the distance x from above equation, the thickness of the boundary layer increases, and laminar boundary layer becomes unstable and leads to the transition to turbulent boundary layer. Here BC is called the transition zone and FG is called the turbulent boundary layer. Now let's move on to the concept of laminar sub layer. This is the region in the turbulent boundary layer zone adjacent to the solid surface of the plate. Velocity variation is influenced only by viscous effects in this zone. Though the velocity distribution would be a parabolic curve in the laminar sublayer zone, in the view of very small thickness, we can assume that velocity variation is linear. And so the velocity gradient can be considered to be constant. Shear stress would be constant and equal to boundary shear stress. Thus, the shear stress in the sublayer is tau 0 equal to mu into dou u by dou y at y equal to 0, which is equal to mu into u by y. Since for linear variation dou u by dou y equal to u divided by y. Now let's move on to the topic boundary layer thickness. It is defined as the distance from the boundary of the solid body measured in the y direction to the point where the velocity of the fluid is approximately equal to 0.99 times the free stream velocity u of the fluid. It is denoted by the symbol delta. For laminar and turbulent zone, it is denoted as delta lam is the thickness of laminar boundary layer. Delta t is the thickness of turbulent boundary layer and delta dash is the thickness of laminar sublayer. Now let's move on to displacement thickness. It is defined as the distance perpendicular to the boundary by which the free stream is displaced due to the formation of boundary layer. It is denoted by delta star. The expression for delta star is delta star equal to integral 0 to delta 1 minus small u by capital U dy. After displacement thickness, now we have momentum thickness. It is defined as the distance measured perpendicular to the boundary of the solid body, by which the boundary should be displaced to compensate for the reduction in momentum of the following fluid on account of boundary layer formation. It is denoted by theta. The expression for theta is given by theta equal to integral 0 to delta u by capital U into 1 minus small u by capital U dy. Energy thickness, defined as the distance measured perpendicular to the boundary of the solid body by which the boundary should be displaced to compensate for the reduction in kinetic energy of the following fluid on account of boundary layer formation. It is denoted by delta star star. The expression for energy thickness delta star star is integral 0 to delta small u by capital U into 1 minus small u square by capital U square dy. Now let's move on to a problem based on the concepts that we learned. The question is, find the displacement thickness, momentum thickness and energy thickness for the velocity distribution in the boundary layer given by small u by capital U equal to y by delta, where small u is the velocity at a distance y from the plate and small u equal to capital U at y equal to delta, where delta is the boundary layer thickness. Also calculate the value of delta star by theta. Now let's try and solve the above problem. It is given in the question that small u by capital U equal to y by delta. The first thing that we have to find is the displacement thickness delta star. It is given by the equation integral 0 to delta 1 minus small u by capital U dy. Here we know that small u by capital U equal to y by delta. Substituting that to the equation, we have delta star equal to integral 0 to delta 1 minus y by delta dy. Integrating, we have y minus y square by 2 delta from 0 to delta. Solving that, we get delta by 2 as the answer. Now let's try and find out the momentum thickness theta. We have the equation theta equal to integral 0 to delta small u by capital U into 1 minus small u by capital U dy. Substituting the value of small u by capital U equal to y by delta, we have theta equal to integral 0 to delta y by delta into 1 minus y by delta dy, which is equal to integral 0 to delta y minus delta minus y square by delta square dy. We have, on integrating, y square by 2 delta minus y cube by 3 delta square from 0 to delta. On solving this, we have delta by 6 as the answer. Now let's find out the energy thickness delta double star. Delta double star equal to integral 0 to delta small u by capital U into 1 minus small u square by capital U square dy. We have small u by capital U equal to y by delta. On substituting that, we have integral 0 to delta y by delta into 1 minus y square by delta square dy, which is equal to integral 0 to delta y by delta minus y cube by delta cube dy, which is equal to y square by 2 delta minus y raised to 4 by 4 delta cube from 0 to delta. On solving that, we get delta by 4 as the energy thickness delta double star. Now for the last part of the problem, we have to find out delta star by theta. We have delta star equal to delta by 2 and theta equal to delta by 6. On substituting, we get 3 as the answer. So as solving the question, we got displacement thickness delta star to be delta by 2, momentum thickness theta to be delta by 6 and energy thickness delta double star to be delta by 4, and the value of delta star by theta is 3. Hence we solved the problem and found out all the necessary values. We hope the boundary layer concepts and the problem discussed at the end of the presentation was clear. Thank you.